Is it on? I think it's on, right? Can you hear?
Welcome everyone to the Friday session. So we have the first speaker is Aike, who is going to tell us about the skydiving algorithm.
Good morning, everyone. Good morning. Okay. Thanks for the invitation. It's a great pleasure to talk here. So today I will present you with a new algorithm we developed over the last 2 years. And it's called skydiving, and more technically, it's an efficient way of exploring some parameter space in the Bootstrap problems. And the motivation is, of course, like, is that not on? Is it on now? Still? Is it? Okay. Thank you. Right, so the motivation is, as we are exploring bigger and bigger problems, we just want more efficient programs. Otherwise, it's either undoable or it wastes a lot of resources. Okay, and so now I'll first review some histories of this just numerical bootstrap and the semi-different programming, and before we dive into the new algorithm. Okay, so history. And so, okay, first, the big goal or paradigm of numerical bootstrap is that we want to explore some parameter space to find the theories that that obey some physical constraint or is ruled out by those constraints. So, so those parameters will be, in general, it will be a relatively low dimension parameter space, such as scaling dimensions of some operators in CFTs or like the OP coefficients. And so the computational process is first to turn the bootstrap problems, starting from crossing equations or some other constraints, and rewrite them into the so-called semi-definite programming problem. And then the semi-definite programming problems will be fed into a solver. So see, we have a parameter space. We first pick a point, and we generate our problem, this computational problem. And it's then fed into some solver. Here, I'll just use this process as fed into a solver. And the process going from, like, see, the end of this arrow to the top of the tip of the arrow is, so you can just think of it as a solving process. I give you a parameter here called mu. Later on, I'll explain exactly what it means. But here, starting from a large mu and sending it to 0 is, you can think of it as a process of how much we are getting the solutions. And at the end of that solver, the solver will spit out some output. And that output is a binary decision of whether this point obeys those physical constraints or not. So now we want to map out where the theories are in the parameter space. And to do that, or just to keep sampling points, well, maybe some guided ways of which points we should sample, and we just map out like where the boundaries of those of this allowed region is. So as you can see, now let's look at the computational cost of this process. So each point will requires the solvers to run once, and then the total cost is, of course, how much time each point takes and how many points we have to sample. And in this way, the number of points we have to sample grows with the dimension of the parameter space. And so both parts can create problems. Like the solver will take significant amount of time if our problem is complicated. And also, as we want to explore more and more parameters, this exponential growth, what we call as a curve of dimension, this number will blow up very soon, very quickly. Okay, so that is the most traditional way, in this community. And then about 2 years ago, Slava and the collaborators significantly find a better way of exploring the parameter space, and that is to replace those binary decisions by a continuous function called the navigator function. And not just continuous, but also differentiable. So that navigator function is designed in such a way, it's a function of p, of the parameters, and it's designed in such a way that within some allowed region, here I draw an island, the navigator function is less than 0, or less than equal to 0, 0 is on the boundary, and the positive outside. So now let's just sample one point in this parameter space, and well, indicating by the navigator function, it's outside of the island, and the goal is to go there's some desired solutions inside of the island. And so first, we still run the solver. Okay, this we can't ignore. We can't omit. But then down there, there's ways to extract some local information, like some derivatives, and then we can use Newton's method to tell us where the optimum is, where the island is. So now, instead of sampling points, we have a much more oriented way to see where we want to explore in the next steps. Okay, so now it's much more efficient in the parameter space. And what the whole method does is we run the solver once, we take our steps, and then at the new steps, we regenerate the STPB, and we run the solver again. So we do this process iteratively, and eventually we'll get inside of the island. So now a natural step forward is, well, we're running the solver, which takes a lot of time, but we're running the solver several times, but it's exploring a relatively small regions in the parameter space. And the logic, then we might think, like, why do we have to do these steps iteratively, separating the process of solving this part and exploring p-space? Why don't we just combine them together, since they look pretty close? So that's the basic idea of skydiving. That is, if we start from here with the initial state of the solver and some initial point in p-space, and maybe somehow we are able to travel down in this 2-variable space and dive into some place within the island. Okay, so that's the general idea and also the motivation. That's to improve efficiency. Okay, and now the rest I will talk about the algorithm, and I'm afraid some bit of it you might find technical and set in a more discussions of computer science. But it's rather vital for us to understand those technical details, as our problems is getting harder and harder, and the numerical world it becomes much nastier, and we don't always get a magic box that solves all the problems we want. So I invite you to go in to view those technical details with me, and so that we have some understanding of what's lying ahead, what will stay efficient in our algorithm, and what might break down. Okay, so now to facilitate the discussions later on, I'll first review review the semi-definite programming and what the current SDPB solver is doing. Okay, so now it starts from the semi-definite programming. It's certain optimization problems. It can solve both linear and nonlinear problems. So most general formulation is that we want to find some variable y, which is a vector, and a matrix value variable capital Y. It's a symmetric matrix, so those are our variables. And we want to maximize our objective functions, which is the inner product between a constant vector B and this variable vector Y. While we want to satisfy these constraints, this equality, where again, little y and capital Y are the variables, and the others are some constant matrix of vector valued constants. Okay. And to take a step back, relate the symmetric programming with a Bootstrap problem. So, in numerical Bootstrap or in Bootstrap, we have some expressions or equations of the blocks and as a constraint, and then we want to apply some functionals on those expressions. And then those alpha, those functionals, is related to this vector variable y, while those constants is related to the blocks. Okay, so going from finally, we want to find the functional such that the functional acting on the blocks is positive semi-definite. And this part, this semi-definite part, it gets translated into this expressions. And the logic goes with if we when this expression is positive semi-definite, if and only if this hand side, which is directly related to this expression through those conditions, the hand side can be rewritten as the trace between some matrices and the y vectors, as long as y itself is also positive definite. So our Bootstrap problems is translated into this semi-definite programming problems, and our goal is to find such a y, such a little y and the capital Y, while the capital Y is positive semi-definite. Questions here?
There is one more variable, a star, and this you did not say it's related to blocks or to alpha.
Yeah, so the A stars is a vector of matrices, and it helps us to relate the blocks and the alphas into this form. So to translate these conditions into this condition such that y is greater than 0. Thank you. Okay, now for those who have experience with numerical computation, this is optimization problems with constraints. And the constraints are this equality constraints and the inequality constraints. And the way we solve an optimization problem with constraints is to add the multipliers. So at first, we write down our objective here, and then we add. So this capital X is my multiplier that I want to use to impose this inequality constraints. And similarly, I have different multipliers for the equality constraints. Okay, so now now X and capital X and little x are the multipliers, and if we demand this Lagrangian, which is a function of the x and y's, if we demand the stationarities of the Lagrangian with respect to x and y's, then we get back to the the conditions that we want to y and little y and capital Y to satisfy. Okay.
It's not quite obvious to me how you're going to recover that y is positive semi-definite by varying in respect to x.
Yeah, thank you. So exactly, if we take the derivative with respect to x, we just get y equals to 0. So that's just constraining this single the boundary surface. I'll mention just in a little bit how we impose the positive part. Thank you. Yeah. So now the theorem of constrained optimization is that the saddle point, a saddle point with, or in terms of all those variables, including the multipliers and the original variables, give us optimal solutions of the y's. So we want to find the stationary point of x, capital X, little y, and capital Y. Okay, and just one more step further is here we are treating y and little y and capital Y as variable, while x and little x and capital X as the multiplier. But they are completely equal, like in equal footing, so we can like exchange their position. We can think of little y and capital Y as multipliers instead. So then, in that case, we'll be optimizing. Let me just. We'll be optimizing in terms of x and capital X instead. There's a minimum. This optimization problem is to find the minimum of the inner product between C and X with some constraints. Sorry, this is capital X. I think I need to just to check, get it right. It's a bit weird. Sorry, B is also a matrix acting on little. Sorry, it's a big packed here, but you don't have to pay too much attention to the constraint. Mainly, it's just now we'll get those constraints by taking derivative with respect to y to the y's. So then the so-called set now, as you can see, one of the objective is a maximum of b dot y, and the other one is a minimum of c dot x. And the saddle point is when these 2 points coincide, when we achieve optimalities in both problems. Okay. Okay, so now let's go to the parts of this. How do we solve such a problem after we formulate it? And this part will involve the positivity conditions. So the interior point method is one of the most successful methods to solve a semi-definite programming problem. And it's efficient, and it's relatively accurate, and it guarantees convergence after a certain amount of iterations. And it is also it's rather relatively suited for a higher dimensional problem, which is our case. And so the SDBB solver we use these days use the interior point method as a subroutine. Okay, and the reason it's called the interior point is, see, this is, I'll use the capital X as an example here. So see, this is the positive regions, and this is the boundary of the positive cone of X. And the interior point method will start from deep inside of the interior, and each time it will take a step and gradually converges to some optimal solutions on the surface. And this is why it's called interior, because it stays inside instead of directly go to the boundary and try to converge on the boundary. OK, and in order to stay inside, we'll need an additional term called the barrier term. So barrier term, it's a term that gives penalty to the Lagrangian when x approaches to the singular surface. Right. So the closer x gets to the singular surface, then the log term blows up, and so it adds. So we put this back. Let me put it here. So we put this back in the Lagrangian, and the Lagrangian now has an additional parameter mu, and so it's the larger mu is the more this term will penalize x and push it into the so-called interiors of the feasible region. Okay, and all right. So finally, including this barrier term, there's one more stationary condition. When we take the derivative with respect to x, and that gives us x times y is proportional to the identity matrix and proportional to mu. So when mu is positive, x and y has to stay positive, and that's how we encode those two conditions. Okay, but so this is a penalty term. It's deformed the problem, but of course our final goal is to find solutions that without considering without this term being there. Okay. So we'll start with a mu large with some initial conditions, initial points of the solver, x and y's. And this is an optimization problem. So we will use Newton's method. All right, just make things easier, I'll rename that big vectors as c, just a single variable c. Newton's method can compute the step we want to take in c. So it converges to the optimal solution, where this is a Hessian matrix, it's the second derivative of the Lagrangian. Okay. At the same time, we'll be decreasing mu gradually. So starting from a large value, we want to decrease mu to 0, so that at the end, this term doesn't matter anymore. Okay. So this is a brief summary of what is the routines lies behind SDVV at some fixed parameter p. So now let's move on to the part that consider how to introduce the p dependence. Now remember, p are some physical parameters, like those, the scaling dimensions, OP coefficients. And so they enter the blocks. And as they enter the blocks, they get translated to those constants, B and C's and capital B's. So those constant matrices or constant vectors becomes P dependent. All those depends on P, and just mention in general, those matrices A's do not depend on P. So we don't have to consider those. Okay, and then they enter the Lagrangians, and so our Lagrangians originally are functions, are mu-dependent functions with respect to C, now has two sets of variables. That's C and P. Okay, so now we want to deal with the optimizations in both variables. Now, it doesn't seem to be too much of trouble. Like we're just doing Newton's method on a bigger system. So what if we just implement the naive Newton's method in both C and P? So like we just include the P's and C's and also the cross terms. So now we're just solving a bigger system. And this is exactly what we did at first, just implement this, the most naive and simple version of the story. And what we observe is that the behavior of the solvers was very problematic. And essentially, there were two problematic behaviors related to P and C separately. Not quite separately, but respectively. So the first is dp. So we are always taking a step in P and C at the same time. And what we notice that, see, when we are testing the new method on a model we know, like the 3D icing, what we found is that we know where island is, and see we were at here, and dp just goes to some directions that doesn't make sense. So we don't know what it's doing. We really wanted to go somewhere, but it didn't. So what went wrong there? And how could we get it under control again? So the first problem is just we get wrong DPs. It's not making progress to our final goal. And secondly, an even more catastrophic scenario is when with our solver, those x and y's doesn't converge. So at some point, the solver almost stops moving. The C doesn't go anywhere; it just stays there. No convergence, and the solver, and that is what we call the solver stalls. So in hot starting, when the solver stalls, we simply have to start the whole process from afresh, like starting from the very beginning, the large mu's initial conditions, and see if we get not lucky next time. But of course, that's not what we want to do. So now, giving you two problematic scenarios, I will first try to give you some explanation of why they are happening, why didn't they happen before, and after describing those, giving you some explanations, I will go to the part that how we are solving those problems in the skydiving algorithm. Okay, so now first, why are they happening? Let's take a wait. So let's see what we're changing here. We're going from the P's. We are going from solving C and the P's separately to mixing them up and solving them simultaneously. So clearly something went wrong when we are mixing those two sets of variables. So now let's compare. We have C and P. So one important reason that STPP so far works so well in most scenarios is that the C, although complicated, high dimensional, but the region have a very nice property that it's convex. So convex optimizations helps STPP to converge. On the other hand, in P space, so we know in the physical parameter space, usually we don't only have a single feasible regions. In the icing examples, we have an island, and up somewhere we also have the continent. It's other large feasible regions. And then the navigator functions is negative both in the island and also in the continent. So then you can see our navigator functions will be something like look like that, or even deeper here. So anyway, it's very obvious that in P space, the navigator function is not necessarily convex fact, most of the case, it's not convex. So now, the non-convexes in P space is reflecting badly on the C space as we mix them up. It sabotages the good properties of being of convexity. Secondly, so we'll say, well, P space is a relatively low dimension space. It's relatively easier to visualize. And then, for example, in the navigator case, sometimes we put bounding box to regulate how we want the solver to move around in the parameter space. So this should be relatively easy to visualize and to deal with, and to make we can impose we can force it to go somewhere by hand. On the other hand, C, which encodes all those big vectors and the matrices, is huge. The dimension is just huge. So even a very, even just the 3D icing at low dimension, at low derivative orders, the dimension will go up to 1,000, 10,000, or even much, much higher. So now it's the other way, is like the high dimensional space makes it very hard for us to do anything to regulate to kind of limit the behaviors of our solvers in the P space. So as we are mixing, we are sabotage the good properties in both in both variables themselves. Okay, so that is one problem that we get from mixing the two variables. And the second problem is we're changing mu. Of course, this happens in STVB as well, but it's even it's more serious for us that we are doing optimization problems. And Newton's method, in general, Newton's method targets the same objective functions. So see, we have a surface. We want to find the optimum point. If Newton's methods will try to take many iterations to converge to the optimal point. But then a changing mu means a changing objective. So we only have some approximations of what the next surface might look like, and we do not know it exactly. So even if we get a pretty good approximation at one surface, but next steps will be pop onto a completely different surface. So it might just be that our prediction from last step is very wrong for the next steps. So that is also one of the factors that contributes that we just get the wrong DPs. Because we're changing our objectives, we're changing our goals and targets all the time. Okay, so those are the part that went wrong. So now I will start discussing the how we want to solve. We might solve those. We might tackle those difficulties. Okay. So the goal is to we want our solver or our algorithm to be efficient, meaning that we want to take we want to reduce our mu, because we have to reduce our mu, and we want to reduce it as quickly as possible to approach the final solution. We want to take relatively big steps in C's and also in P, so that we get good enough convergence. But at the same time, we want to take some meaningful steps. Especially dp, dmu, dxc. we want to take meaningful steps, meaning that we want to make progress towards our final goal instead of letting P wander about into a region that is, instead of wasting time there, and wasting time there is a better scenario, as sometimes it just goes completely off and never converges to our final solution. So we want to achieve both. And the way we will quantify those properties, we have a few parameters, important solver parameters, and to tell us how efficient or how meaningful. So one I have discussed extensively is parameter mu. It's the faster mu decrease, then the faster we are making progress to the final solutions. And secondly, and thirdly, are two parameters I'm going to introduce just in a minute. One is called alpha. I'm sorry, but this alpha is not the functional alpha. It's a scalar parameter called step length. And this R is an arrow term. And this arrow is describing how good enough we are solving these equations. So R is just the difference between x times y, the product between x and y, minus this identity matrix times mu. Okay, so those are the top most important parameters we're going to use to describe to measure how to change the states so that it's both efficient and meaningful. Okay, and now let me tell you more about especially what this step length factor alpha is.
Can I ask a bit of a philosophical question? So
Yes.
You have now variables xi, p, but you also have this mu,
Yeah.
which also has to flow to 0, but this flow is very different from the flow of p and xi because it's not governed by
No, it's not dynamical.
any Newton step or anything. You know it has to go to 0, but it's not really a variable of the problem. Is it unavoidable? Is there some fancy way of doing things in which you treat mu also as a variable on par with parameters p and xi, so
Yeah.
that you flow now in the space of 3 parameters?
So, okay. So first, so in terms of constraint optimization, we get equality constraints and the inequality constraints. In general, okay, this is based on my own knowledge, but I have not seen like a dynamical Lagrange multipliers on the inequality constraints. The reason I'm not exactly sure why in general, but in our case, see, we treat mu as a dynamical variable, and then we will compute like how d mu changes based on some differential equations. But then we still have, like, we want to keep x, y positive, right? So there are still constraints that mu cannot go to zeros. So we still have to penalize the mu terms again. And so this is so first argument is I don't know if there's it is doable or efficient way of imposing this extra constraint. Secondly, I also used to experiment with some other Lagrange multipliers in this problem, which is a single scalar versus the 10,000s of other variables. And what I found is it's just the behavior is super hard to control. I think, like, in general, going from high dimensions projecting to some low dimensions, there's a scale problem, and numerically, it makes it hard for this low-dimensional object to behave properly. Yeah. Thank you. Okay, now let's discuss the step length alpha. So what the step length means is that, remember, every time we are taking Newton steps, we are updating the matrix y, capital X and capital Y. And we want to keep X and Y's positive semi-definite, which is not guaranteed by the Newton steps. So what alpha does is it just scales down, if necessary, on the steps we calculate from Newton's method. So this alpha will be greater than 0, less than or equal to 1, so that we ensure the updated X and Y's remain positive. So in the algorithm, what happens is you determine your next mu's, you use your Newton's methods and solve for X and Y, for dx's that include the dx and dy. And then the algorithm will calculate this alpha, takes a value from 0 to 1, so that the updated X remains positive semi-definite. So, okay, so that's what step length is. Now, more pictorially, let's again look at these pictures where this lower half is positive regions of X. So now, yeah. Sorry?
Naive question. Is that simple to check that the matrix is positive? I thought this would be very expensive.
It is rather expensive. So, yeah, so it takes it, because it involves taking the inverse of the matrices. So it is expensive. But it is, I see there are other expensive computation in SDVB already. So it's expensive, but it does not change the whole complexities. Yeah. And, right, so it's expensive, but it's necessary, and I'm telling you why it's necessary now. Okay, so let's see, at some stage, our solver is deep inside of the positive regions. We want to converge to a point on these boundaries. If we get the steps right, we'll make good steps towards the optimal solution. But remember, so x, y equals proportional to the identity matrix. This is not a linear constraint, and it's possible that at an early stage we can get a very wrong steps. It's wrong directions, and it steps out of the positive region. And what alpha does is it scales it down. It scales it down and make it stay inside of the positive region. So that's what alpha is doing. But then let's look at the part, like, if we continue going from this point, and we see next step, it make a good decision, like it knows that the optimal solution is here, it's necessary to take a step towards that direction. But look at here, it's hitting the boundary again. So now a different alpha will scale these steps down. But as you can see, we are approaching the boundaries, and the closer we get the boundary, the smaller alpha becomes. And if the solver is too close and it's unable, it's just convergence, like gradually convergence on on the boundaries, then the steps will be very small. And at some point, the solver might just not able to move at all, and that is when stalls happening, and that's why alpha is important parameters to characterize how close we are to the boundaries and how, like, because when it stalls, it's very hard to kick it out, and we want the essence of interior point method is to avoid those points, to ensure good convergence. Okay, so that is what alpha is characterizing, and we want to avoid the scenario when alpha becomes too small. So this kind of stalling behaviors happens even for standard SDVB at fixed parameter p, when we change mu too fast. So we change mu too fast, our objective is changing too fast, we might just be making wrong steps in the solver state, and it stalls. It's getting to the boundaries, it doesn't know where to move, and it stalls. And also, like some audience might have experienced with hot starting, where the stalls also happens. And hot starting meaning, let's take the navigator function as an example again. So hard starting meaning we have solved the, see at fixed p we solved it for the c's or x and y's. Now it seems that next time we're just taking a small step in p's. It's almost like very similar SDB problems. We think that we can recycle the solution. I'll use this star as a solution. Recycle these solutions and just going from there. Instead of going deep inside of starting everything afresh, we're just going from there and go to a different optimal solutions that corresponding to the new SDPV. And what many of us have experienced that this also stalls. Even just changing P a little bit, the stalling behaviors can occur very frequently. And so in order to have a robust enough method using the navigator ideas, we sometimes have to we have to give up hot starting, which adds the complexities or like, use of resources. And okay, so those are two scenarios I'm giving you that when stalls happens. First is when mu changes too fast. Second is when P is changing and we want to recycle our solver state. And now what skydiving is doing, we're just changing everything at the same time. So we're changing the states, we're changing mu, we're changing P. And this is when stalling just happens so frequently that it becomes one of the vital problems that we have to deal with. Okay. Now, let me finally start with the algorithm. So there are two most important subroutines in our algorithm that deals with those issues I mentioned. One is called centering. It's a centering step, and a second, I should erase it. And the second one called scanning step. Now I'm going to discuss them one by one. The second called scanning. So during centering steps, we'll be changing C while fix P and mu. But in scannings, we'll be changing everything at the same time. And okay, so let's start with centering. So as I've described it in the other whiteboard, although the ideal scenario is that we change everything at the same time, which is the initial motivations of designing a skydiving algorithm. But what we notice is it's really a hard problem. So it's still necessary to some extent to separate the two updating stage. And what centering does is it does not update the other two parameters, the P parameters and the mu parameters. It just focuses on getting the right C. So what we do in these steps is that we're solving the optimal condition, the stationary condition for C only, while fixing mu and P. And after the solution, this solution can be said to be parameterized by a mu and P. So we get rid of this large variable C, and instead we parameterize it by a scalar parameter mu and some low-dimensional parameter p. Okay, so this is effectively reducing the dimensionality of our problems. It's reducing it from like a huge parameter space to a relatively manageable one. So then at this stage, our Lagrangian, we can rewrite it so our Lagrangian with those local stationary solutions becomes functions of mu and p alone. So this is, we can think of it as a finite mu navigator function, a finite mu version of the navigator function. Okay, so now it's easier to deal with, and we do we observe that now after the separation of the problems, we get significant improvement in the predictions of dp. So it stops with those wandering off wrong direction behaviors. Okay, and the criterion for in the algorithm that's that we are close enough, that our state is close enough to the stationary solutions, is characterized by this arrow R here, because this is describing how well we are solving these equations. So as the arrow becomes small enough, then we can confidently say like our state, our solution in C, sorry, our state in C has converged enough, closely enough to the optimal solution. Okay, so that's a centering step that helps us to fix some issues. And next, now we can forget about C for a while, and we focus on P and mu's. Now, we know that we are starting mu from a large value, and the end result is that we want to get to the navigator surface, which is mu equals to 0 surface, and we want to land in some optimal solution, say here. And the larger mu is, the more deformed the finite mu surface can be. Like it could be just completely different, and if we use this surface as surface to approximate the final point, then the dp is just completely rubbish. So we do not do that. So then the first step is that we need a decision when to first start updating P. So this will be the first, the surface that we reach, see here. The first mu surface that we feel comfortable enough of taking P steps now. And this is a simple condition, like we just want to reduce mu to some threshold when we will start updating P only when mu has decreased to some has decreased enough below some mu threshold. So that's just a single parameter, that's easy. And now the main body of the scanning algorithm starts as following: is, see, now the solver is at some surface mu. What the solver wants to do is we need to find the next surface we want to move, like how much we want to reduce mu. Now, the decision is, how do we know which surface? Yes, we want to, we want to reduce it efficiently, but we don't want to get completely wrong information. So which mu prime? And then this relation, we can draw a relation. It's a qualitative relations between the step length alpha and how much we're changing mu prime, which I'll label the ratio between the new mu prime and mu as beta. So the smaller the beta is, the faster we're changing mu. And alpha, again, alpha is characterizing like how safe the solver is. We don't want it to approach the boundaries, which will make everything, will subtouch everything. Okay, so at the origin, when beta equals to 0, that's just going from here directly to the mu equals to 0 surface. And that is a too risky a move, and usually ends up alpha being 0. That's just shoot it off on the boundaries. So we don't want that. And then beta equals to 1 is our current surface here. And looking at the vertical axis, alpha equals to 0 is here, and alpha equals to 1 is the best we can get, like the safest step we can get. So in general, the relation is a monotone relation. It kind of looks like this. It's not linear, but it's a monotone. Usually, it's a monotone. A monotone relation. Okay. So given this relation, what we want to do is we want to the algorithm will choose some threshold on alpha. And we want to get the beta that first reach this alpha. That is, at first we start with a beta minimum, and maybe we shoot it here, like just a constant. We start from here, and then we calculate our alpha corresponding to this mu prime or this beta, and we found it alpha too small. And so we will not take this beta. Instead, we'll increase it by some amount. We'll go to the next one and check alpha again. And this is what we mean by scanning, which is scanning from some beta means and gradually increase. And we take the first betas that satisfy it goes above this lower bound. And in this examples, we'll pick the beta here. We'll put the beta here. We are satisfied that alpha is big enough. We feel comfortable in moving in parameter space, in C space, in any space. And so this is our point. So this is a good scenario in general. Most of the time this happens.
Can I ask a question?
Yeah.
And what about the mu threshold? Is it just some parameter that the user should supply, or how does it work?
Yes.
Okay.
And this different, a second scenario is when we don't get good behaviors in that is beta, no matter what beta we choose from 0 to 1, alpha is just small. And that is, here you can think of it as the solver is already very close to the boundaries. So no matter what beta we choose, the solver is in a very dangerous and risky stage. And no matter where it goes, it might stuck, it stalls, it hits the boundaries. So none of the value from 0 to 1 is good enough. Then at this stage, we have to increase beta. Questions? Okay. And increase beta, increasing mu, that's penalizing this surface more. And so effectively, larger mu, we're pushing the solvers inside again. So we'll give up any updates in P. We just increase mu, get the solvers to a good state again before we do anything more experimental. Okay. So that's what scanning does. So scanning help us to choose a good mu surface we want to go. And when it's problematic, it also allows it to escape from the bad behaviors. OK. So that's so those 2 points. In the algorithm, the algorithm will alternate between the centering steps and the scanning steps. So every time it's after taking a step, it's first to do scanning. So that's we get rid of some very hard to get rid of some high-dimensional variables, hard to deal with. And after that, we are prepared to do the scanning steps to actually make progress in terms of the solver and also in terms of the parameter space. Okay. So, okay, I should tell a metaphor here, but not sure if it's a good one. So my take of the alternation between the centering and scanning is like, imagine a pilot flying some planes on some complicated terrains, and there's a valley that the pilot wants to go. But unfortunately, he's equipped with a very 40 meters. And if he keeps adjusting his meters, measuring his height, and at the same time turning randomly around, he's probably going to get lost or have some accident very soon. So instead, let him focus, like stop the planes, just stop at certain height without moving, focus on his meters, turn it, okay, and then take a step. And after after flying around, like descend a little bit, wander a little bit, now let's take a look at the meters again, and of course it goes around again, and then he turns it again, and repeats this process. So it's a several way of finding solutions in all different space. Okay. Now let me just briefly outline some results we had, I think, as demonstrations of the performance. So in our paper, wrong pen. So in our paper, we tested our algorithms on the 3D Ising, and where the dimension of P is equals to 3. And we also tested on the 3D O3 critical point, critical model. And the goal there is to to upper bound the scaling dimensions of the rank 4 tensor. That in particular, we want to find if it's relevant or irrelevant or marginal. And so Martin and Benoit, who talked last week, they are testing the new algorithms on their, ON cross O2 model. And I think they went up to derivative order lambda equals to 31. And finally, Matt was also in the audience, I hope. Thank you. Is testing the new algorithm on the GNY model. Okay, so now I'll just present discuss our results briefly. So starting with the Ising model. Well, first, take a look at the performance, complexity, computational resources required. So first, the Ising, let's take a look at the number of iterations. So for us, the important number of iterations are to characterize the computational resources is the number of steps we have to take in the P space and the number of steps we have to update the solver variable C. Okay, so for example, for a single SDP, for a single STPB run at a fixed P requires, its complexity is characterized by how many steps in C it has to take. So, and for Ising at lambda equals to 19 and 3D search, it's usually about 200 iterations for a single STPB. And now, the number of steps in P space then, for example, the navigator functions, I think it usually takes 100 steps. Well, without hot startings, then the navigator will have the whole complexity will be this number here times the number of times we have to update the update p. And for us, we will have one big steps here as we decrease mu fixed at fixed p as fixed p. So we'll get about 200 steps in X's in the first iterations at the initial point of p. And then in later iterations, this number decreased down to about 4 or 5 iterations, which are the centering steps. So each time we'll only spend 4 or 5 times in the internal solvers when solving for X's, and the rest are just updating in the P space. So we get rid of all those areas down there and improve the efficiency. Okay, so that's a general. That's a number of iterations, and in terms of how the solver behaves, as mu describes how much progress we are making how much progress we are making when solving, working towards the final solutions of the solver. So let's take a look of how mu behaves. So we wanted, yeah. Okay, thank you. So let's look at the log plot, the log mu, and yeah, it should. We want at the end we want mu to be very small, so we want it to go somewhere here. Okay, and so first we reduce mu from a very large value to some threshold value. So we ignore the first step, it will just dive down here. And then the solvers will decrease it according to what the scanning algorithm tells us. It changes rates. When it's safer, it's decreased faster. When it doesn't feel safe enough getting to a boundary, it changes rate, slows down. And at some point, it's possible that it finds itself in a state when it can't decrease mu anymore. It just can't decrease mu at all. Then it'll climb up a little bit, and then it'll find itself in a region close enough to the final optimal region. Then it dives down very quickly. Okay. So that's a general behavior of what the solver does. Okay, and in terms of numbers, we get a bound for delta sigma, lower bound for delta sigma at lambda equals to 51, and it's greater than 1 by 1.126. And okay, and that is for the icing. I think the improvement is, okay, I have to be honest, the improvement with the previous result is not huge in terms of the digits, but it's true that we are using much less resources. Okay, and so I think 2 digits, 7.5 or 5.7, the last two. Okay, and briefly mention the results for O3. I think the original paper was with a tip-top algorithm used more like the binary ideas, like just sample points and trying to find the boundary. And I think in the original paper, they report their result and lambda equals to 35. But thanks to the new algorithm, we didn't have to go up to 35. We were able to prove that a rank 4 tensor is relevant even at lambda equals to 19. So that is 2.9998. So it's already proved that the operator is relevant, and so we are running at a lower we are running at a lower lambda, and we are using less resources. Like we're taking fewer steps. Okay, so that's our results. And how many minutes do I get? Wrap up. Okay, good. Okay, so wrap up is I just have a few comments or remarks and the outlooks. Okay, remarks. So to sum up, using the skydiving algorithms, we have shifted the computation bottleneck from SDBB to just generating SDPs. That is, we shifted this chunk of the computation resources to just how many times we need to update DP, and which is equivalent to how many times we have to regenerate the simulated programming files. And so, now, so SDBB used to take the majority of the computation, and now for the skydiving algorithm, this part takes about 70% of the time. While the hard computation used to be hard computation, now takes 30% of time. And even among that 30%, half of it is spending on input and output. So the reading and the writing out of the numbers instead of doing the hard computations. So this part is computation-wise or technical-wise, this part is subject to further optimization. They are not the hard complexity issues we have to deal with in an algorithm. Okay, so that changed the strategies, or like the point we should, like the focus of optimization. Okay, and so that's in terms of efficiency. But I should mention that so far we have tested our algorithm only on a limited number of models, and of course there are many more models, more complicated, and the scenario might get nastier if you want to try higher derivative orders. So, well, we invite you to try our algorithm on other models and tell us if you run into any problems, and we'd like to hear about it and see if we can further improve it. And finally, the outlook part is now we are able to exploring the parameter space P, but there are more parameters which there's one parameter, this parameter lambda, which is the derivative orders, which we know, like, as we increase the derivative order, the size of the problem grows drastically. So can we take the lambda, take lambda as a variant parameter as well? That is, can we extrapolate from a lower lambda to higher lambda efficiently? And that will that will improve our numerical bootstraps algorithms very dramatically. Okay. I think that is the end of my.
Just one naive question. So if P is, for example, 5-dimensional,
yeah,
and I want to look for kinks and edges and so on, is there a simple way? Because, yeah, otherwise to visualize it's very hard still.
Right. So right now, the two options offered is one is to minimize the. I picked the wrong one. First is to minimize the navigator function, and the second one is to maximize this objective, which you give directions you want to optimize, and then you find the largest you can go in terms. Yeah, so kings, since we don't know the directions, so I don't think it's easy to implement yet. Yeah, but right. Yeah, we need some consideration. Thank you. Yes.
When X moves to the boundary of the allowed space, so how many eigenvalues become 0? Is it just typically 1 or
It depends. Let me think. So, so it's a whole boundary. So I suppose there are many different singularity points. The different components will go to approach 0. So it depends on, are you asking if...
In the optimal solution?
The optimal solution?
Yeah.
Okay. So the optimal solution is when xy equals to mu times lambda, mu times the identity matrix. And as we are reducing mu to 0, then the whole thing just becomes 0. So at least the x times y, the product of them, is identically 0 everywhere.
So all eigenvalues?
Yeah.
So how did you manage to get the result on delta T4 with the lower lambda? Is a bit counterintuitive. If the setup is exactly the same, your algorithm just works faster than the previous algorithm, but it shouldn't improve the delta. So they were too conservative. Maybe they were too conservative at small lambda. They could not.
So you can see this is approaching 3. This is 2.999. So in order to get that many digits, I presumably is a TikTok that they have to scan for too many points to get that many digits.
So what was their result at lambda equals 35? It was not as close to 3. Ah, okay, now I see. Thanks. Any other questions? Well, you have a question, Ning? No? Okay. Well then, let's thank Eike. Excellent talk. Yeah.
Thank you.